Hi, students. This YouTube video is over, lectures over chapter 10 on oscillations. Okay, so if you recall, I told you a few times this semester, I believe as far back as the first video, that objects move three possible ways. And that is translation, rotation, and oscillation. Okay, so and we're studying mechanics, which is the study of objects in motion. And so how do objects move? They move three possible ways. We have discussed translation throughout the majority of this class. Translation is that the object moves as if its entire mass is located at its center of mass. All right, rotation, we talked about that in the last two chapters. And so in the last two chapters, with translation, you consider an object like a point mass. But with rotation, you have to think of the object as being more extended. All right, so let me kind of just draw this out a little bit more here. So again, as we talked about in the past, we talked about translation. All right, again, an object moves as if all of its mass is located at its center of mass. I'm not writing today. All right, we consider it like a point particle. Has really no extension. When we talked about conservation of momentum in two dimensions, we refer to momentum of point particles. We didn't have to talk about things like rotation. But the second type of way objects move is rotation. All right, so this is particularly chapters 8 and 9. We just got done talking about. All right, so we have to consider an extended body. Where all parts of the body revolve about a common center of mass, or sorry, common, not center of mass necessarily, but a common axis of rotation. All right. Well, what's nice about rotational physics is that, well, you imagine you have a body rotating, let's say about some axis. We'll say this is the central axis, and I'll consider, let's say, 2 points on here. So here's the central axis, and I'll consider point 1 and point 2, and the body is rotating at some angular angular velocity omega. Well, as it moves around, let's say 1 and 2 are lined up on the same radio. Well, 2 is to the right of 1. Well, as it moves around, if I'm standing at 2 and a friend of mine is standing at, if I'm standing at 1 and a friend of mine is to my right standing at 2, that friend of mine is going to continue to be at my right. You know, every point on the object is going to have a relative location that's not going to change. All right, so the relative location of one point with respect to another is not going to change. The object is solid. All right, but now we consider what is called oscillation. What is that? And that's what this chapter is about. For oscillation, we let the body possess elasticity. So, for instance, if you imagine a body, now, if I look at 1 and 2, these particular, you know, if there's oscillation going on, parts of the body may move with respect to one another. And so essentially the body may be elastic. So different parts of the body will move with respect to one another, often modeled as sinusoidal motion. I.e., described by a sine or a cosine. We may refer to this as periodic motion, in fact. It repeats itself. Back and forth, over and over again. Periodic motion. So we typically will think of maybe the part of body 1 and body 2 constantly back and forth with one another, you know, as the object moves. So there's an elasticity now. Typically, sometimes we refer to these as vibrations. Okay, so that's what we're going to study in this class. So imagine if we have an extended body, how might we model it? Well, we might model it as little masses on springs, little mass elements attached to springs. So this elastic body may be modeled as masses attached, or we'll say mass elements attached via springs. Or say, well, connected, we'll say, by springs. So some elastic body, if you look at it closely enough, you might say, well, maybe I might think of this as M1, and maybe an M2, and maybe there is some sort of a imaginary spring that I can kind of think of between the two. So M1, say M2, and maybe there's a spring you can think about between M1 and M2, and maybe M3, M4, and you can go in 2 dimensions even. M5, M6, and there's really spring here too. You know, keep going on. You know, you get the picture. This whole body can be thought of as a bunch of point masses or a bunch of mass elements connected by springs. We can continue drawing or making our drawing to have an extended body. And these bodies all move about each other, and they form kind of an elasticity. You know, the elasticity is given by springs. Each spring has some sort of spring constant. Let's say this is K12, K23, maybe they're the same, K34, so on and so forth. So each one of these has its own spring constants even. And so you can characterize these as, you know, masses on springs. We've talked about the spring force, a mass on a spring back when we talked about Hooke's law back in chapter 4. We talked about forces. So again, we can model an elastic body this way. Well, if that's what we're after, why don't we start with the simplest possible mass or simplest possible scenario? How about one mass on one spring? Let's try that. So we're doing mass on a spring. All right, so what's our picture going to look like? Well, we have a wall, and let's say a floor. And we have a body, some mass, we'll just call it M, and it's sitting in an equilibrium position. It's attached to a spring, but it's sitting in equilibrium, doesn't want to move. There's no reason for it to move. It's happy, it's at equilibrium. We'll say the spring is given by a force constant K. We've talked about that in the past, so we'll review it briefly in a moment. But we'll say there's a spring constant K, and there's a mass M. And we'll kind of imagine for the moment that this, you know, we'll call this the x-axis. And this is, let's say x naught. See, because it's an equilibrium position. Where the system is at rest and relaxed. Okay, so it's at rest, it's at relaxed. There's no force being felt by the mass due to the spring. It is pretty much in a state of equilibrium. Okay, now we know that, you know, this is a mass M. M is mass in kilograms. K, we talked about this before. This is called the force constant, or sometimes we refer to it as a spring constant. And that's in newtons per meters. All right. Now, let's imagine now that we're going to compress the spring by some displacement x. All right. So we're going to imagine that this is my initial location of the body. I'll make this dashed lines because this is where it was originally. Initial location. What I'm going to do now is I'm going to compress it in by some amount x. All right, so let's compress the body. Let's move it in. So now I'm going to compress by an amount x. Same mass, and now the spring is compressed. All right, and what did I do? Well, I moved it by some sort of an amount x. That's the displacement. All right, so now we're going to displace the spring by an amount x. Spring still has a force constant K, and again, that is a constant. All right, so let's compress the spring by a displacement X. All right, so we're gonna compress it. Now, we found out back in chapter 4 that there's actually a conservative force that'll be felt by the spring. It's a resistive force called the Hooke's law force. So the mass, so the spring exerts a resistive force based on Hooke's law. And remember what that was, that's the force, this is the force that's felt by the mass, force on, by the spring on the mass is negative Kx. It's a linear force. The more you compress this spring, the greater that force is. K is a constant, it's a linear force. The negative sign just means that the force is resisting the displacement. So whatever the displacement is, the force is going to be pushing or pulling the other direction. Now, remember what we said back in chapter 6 when we talked about energy. We said we can compute the work of any kind of a force, and we know if we can make a diagram, we can make a force displacement curve, that the work is the area under the force displacement curve. So any curve, you have to you can find the area, you can find the work by the area under the curve. In general, you'd have to use integral calculus in order to be able to find this. But fortunately for us, this is a nice linear curve. So I'm going to neglect the negative sign now, and we're going to look at what this curve looks like. So if x equals 0, this is the displacement axis. This is the force axis. If x equals 0, of course, the force is equal to 0. Means it's at equilibrium. I mean, there's no force that's pushing back on it. Now, as we go along, we find out there's a linear relationship. And so at some x, say this is my x, my displacement, what I have is a right triangle. And I say, okay, well, I want to find the area of that curve. Well, it's a triangle, isn't it? The height of this triangle at any given x, the height of this triangle is kx. So the work, it's the area of the triangles. It is base times 1/2 base times height, right? So again, I don't need integral calculus. I have a nice simple figure. So the work is going to be 1/2 the base times the height of this triangle, or 1/2. Let's see, what's the base? It's x. What's the height? The height is kx. That means the work done to compress this spring by an amount by displacement x is 1/2 kx squared. The work required to compress the spring by a displacement x Let's see here. Okay, so, and in fact, this is actually the same work that would require to stretch the spring by an amount X. I happen to be compressing it, but I could also be stretching it by an amount X as well. It doesn't matter. So in fact, I can say compress or stretch. It works the same way. Okay, so it is symmetrical. So I find out that the work is equal to 1/2 kx squared. Now I also told you back in chapter 6 that the work chapter 4, I guess, that the force is the Hooke's law force is conservative, just like gravity. All right, so the Hooke's law force is a conservative force. Therefore, hence, it has an associated potential energy. So say the potential energy is 1/2 kx squared. So when you hold this mass under compression, it's going to have an entirely potential energy 1/2 kx squared, zero kinetic energy. Now what happens? Well, the equilibrium, the system wants to be at equilibrium. So it wants to try to restore itself to equilibrium. So it's going to unfurl. The moment you let this mass go, it's going to take off, and potential energy, this is the maximum potential energy in the entire problem. 1/2 kx squared, because I'm starting with this kind of compression. I release it. It'll go back to equilibrium. And as it goes back, it's going to convert all of this stored potential energy, 1/2 kx squared, to kinetic energy, 1/2 mv squared. It'll convert all the potential energy to kinetic energy, and it'll get back to equilibrium. But the problem is, when it's at equilibrium, it's going to have this maximum kinetic energy. So it's going to have its maximum speed. So it's going to blow right through equilibrium. And what's it going to do then? It's going to start stretching. It'll go to a maximum stretch of 1/2, and it'll go right back to a maximum stretch of x. So it'll come right back over here, and it'll have a maximum stretch of x. And it should be symmetrical, but right now, that's better. All right, so it's going to have a maximum stretch of x. It'll temporarily stop. When it temporarily stops, it'll have potential energy 1/2 kx squared again, zero kinetic energy. It'll then try to come back to equilibrium. It'll go through equilibrium. When it gets to equilibrium, it'll have no potential energy, entirely maximum kinetic energy, and it will be at equilibrium, but again, it'll have maximum kinetic energy. It'll blow right through equilibrium, all the way back to maximum stretching again. And it'll just continue doing this back and forth. And given I have essentially, I'm going to assume always that there's no sliding friction. So throughout this entire chapter, I am going to assume no sliding friction. This is a perfectly frictionless surface. Go back and forth. I'm assuming at this point, right now that the system has No friction at all. So it's entirely conservation of mechanical energy. Conservation of mechanical energy applies. Because, again, the Hooke's law of force is conservative. Only conservative work is being done. All right, because that means then that there's always going to be an exchange between kinetic energy and potential energy with no energy loss in the system. Just like, you know, when you did your lab with the mechanical energy with the track, that track with a skater on it there was no energy loss. So it's going to have maximum gravitational potential energy, and then the skater will stop, and then the skater will go down to the bottom of the track, have maximum kinetic energy, zero potential energy. Then it'll go back to the top of the track, have maximum potential energy, gravitational potential energy, zero kinetic energy, and back and forth over and over again. This is pretty much the same kind of problem. It's just that, you know, with gravity is a conservative force, while Hooke's law force is a conservative force. All right. So when you see this energy conservation is back and forth motion, this is an example. It's called simple harmonic motion. Referred to as SHM. Simple harmonic motion means this system, this mass in a spring, is going to go back and forth with no energy loss. It is going to go forever. Okay, that's what that means. It's going to go forever, and it's going to go in a nice back and forth periodic motion. Simple harmonic motion. Now, I have shown this entirely through an energy argument. The question is, can I use Newton's second law to show this? So that's what this chapter is about, to be able to actually try to model this kind of a system with Newton's second law. What I've given you is an energy description of it. And we're perfectly well suited to do that analysis right now. All right, so can we do this with Newton's second law? So again, I'll redraw my picture, I guess. Again, no friction of any kind. Okay, so again, this is my equilibrium position. We'll say X naught. And we'll say that the way I have this drawn, we are compressed at some X. So compressed at some X, this is X naught. All right, so what's happening here? Well, how do I apply Newton's second law? Well, we're going to consider this the X direction, all right? And so what do? Well, I say the sum of all forces. Again, we're going to apply Newton's second law. See if we can do this. That says the sum of all forces in the X direction is what? Mass times acceleration. Now, I'm not going to write acceleration in the X direction because there's only one acceleration going on in this problem, and that's in the X direction. I don't expect to have any kind of motion through the floor. All right, so that's really what Newton's second law. So what forces act on this system? Well, the only force that is acting on the mass is Hooke's law. And of course, it acts to oppose the acceleration. That's the only force that is on the left-hand side of the equation. So negative kx equals ma, or I can write that ma plus kx equals 0. We remember, though, that a is a function of time, and x is a function of time. Okay, let me clean it up a little bit. So I have A plus K over M times X. Well, let's be official here. A of T, I'm dividing through by M, by the way, plus K over M times an X of T equals 0. All right, so I have the equation for Newton's second law. I don't have any friction in the problem. The normal force is not going to do anything for me. So this is pretty much all I have. I have one equation. But the problem is I'm underspecified. I have two unknowns. I have two unknowns, A of T and X of T. So I'm in trouble unless I can figure a way out of it. And so how do you figure a way out of this is to remember from chapter 2, there's a relationship between these two. All right, so let's revisit that. So we recall from chapter 2 that the velocity, I'm not going to put vector hats on right now. We'll just kind of think about one dimension right now. The velocity is what? Well, the velocity officially, the way I did it in college physics speak, was delta V, so delta X with respect to T. What I want to do right now is I want to look at instantaneous variables, quantities. And so I really want to employ the notions of calculus. I know that we don't use calculus in this class, but I want to employ the notions of calculus right now. So I really want to consider V as really the limit, as considering smaller and smaller delta T's to the point of being infinitesimal of delta X over delta T, and we refer to this limiting process as the X dt. So we exchange deltas for D's. That means that is the slope of the xt curve, or what we call actually the velocity at that very instant of time. At any instant of time, that is the instantaneous slope of the curve. That is the instantaneous velocity. But we can go one step further. Remember, the acceleration we know as delta V with respect to T. But we want to do, again, instantaneous acceleration. So I would say what? I would say, well, A is the limit as delta T approaches 0 of delta V with respect to T. And what is that? Well, that would be dV dt. Again, this is the instantaneous slope, or the instantaneous. We call this a first derivative. So I would say this is the first derivative of the position with respect to time, or the first derivative of the velocity with respect to time, right? So this would be, for instance, the first derivative, as they say in calculus, of the position with respect to time. And of course, this would be the first derivative of the, I'm sorry, not position, this is velocity. And this one up here would be the first derivative of the position with respect to time. That's how you say in calculus speak, right? And so it is what's called a first derivative. It is the first order slope. We say its order is 1. Now let's look at something interesting. We said the acceleration is the time rate of change or the first derivative of the velocity. But wait a minute, though, we know the velocity is the first derivative of the position. So I can make a substitution. Instead of writing v here, I can substitute that dx dt quantity, and I can actually write that the acceleration in this particular case, again, we know it is the time rate of change of the velocity, but that'd be the time rate of change of what? What's the velocity? Dx dt, or we can write this as a second derivative of x with respect to time. Okay, again, this is all calculus notation, but I'll show you why this is important in a moment. Second derivative of the position with respect to time. All right, so what does that allow me to do? Well, where I see A of t, I could substitute this. So I could substitute for A of t, because I know the relationship between A and x. So what happens when I do that? When I do that, I find out that my Newton's second law equation, I mean, what is it? It's A of t plus k a over m times x of t equals 0. And I also remember that a is the second time derivative of x with respect to time. So substituting, I get that the second time derivative of x plus k over m times x is 0. Great. I now have one equation and one unknown, x of t. In fact, I'll be explicit that this is a function of time. That's great. One equation, one unknown. The problem, though, is that this is what is called a differential equation. This is a second order differential equation. That's the problem. Well, okay, so first of all, what is a differential equation? Okay, a differential equation is an equation where the terms all have different orders of derivatives with respect to the independent variable. Okay, so for instance, this first term is second order derivative. This term is 0th order. The function itself would be order 0. See, each term here has an order of a derivative with respect to the independent variable. All right, so differential equations is actually the highest math class taught at the college. So it's generally very difficult to solve a differential equation. All right, and so we'll talk about that, and then, again, so differential equations, if you look in the catalog, school catalog, look at the math department, differential equations is a course so it is the highest level math class taught at the college. All right, so you need to have calculus 1, calculus 2, calculus 3, and linear algebra in order to take this class. It's a very beautiful class. It has a combination of everything you've ever studied in math all in one course. So people like me, I highly enjoy it. But again, it's a class that you really have to have all your ducks in a line mathematically to take it and to do well. All right, and so the question really comes down to is, well, you always have to ask yourself the question is, the central question of differential equations. Can I find the unknown function x of t? Okay, that is not always doable. This is in general very hard to do. Okay, so some cases there's methods. And I say differential equation, I'll call them DEs. Okay, some methods exist to solve them, like Laplace transforms, or there's a method of undetermined coefficient, some other methods learned in class. Sometimes you just have to guess. I mean, I'm not even kidding. Sometimes there is a famous mathematician's name next to a differential equation. That means the differential equation is hard. Some are unknown. For instance, there's a differential equation called a Navier-Stokes equation. Navier-Stokes equation is basically what governs turbulence. There is no known solution to that equation. If you could find a solution, you would solve turbulence. I'll tell you how hard turbulence is. Albert Einstein, toward the end of his life, he was saying, and he knew he was getting close to death. He said, well, when I meet God, I'm going to ask him 2 questions. One is, can you explain gravity to me? And the other one is, can you explain turbulence? And he said, I think I'll have the answer to gravity. So essentially, turbulence is so difficult that in Einstein's mind, not even God could explain it to him, right? And so the idea is that that's an unknown differential equation, and it if you can figure it out, you get $1 million, and you solve an extremely important problem. You would never have to worry about, not being able to determine, let's say, the weather in the future any longer. You'd have a complete understanding of any kind of a system that today has turbulence. With turbulence, we have, chaotic systems, mathematical chaos and all kinds of other interesting things. So anyway, this is differential equations is, like I say, generally hard. So the question comes down to, if you can find an answer to differential equation, if you can find the solution, then there's a nice theorem that says that that is the only solution. So if you can find the solution, x of t, then the existence and uniqueness theorem so it's the xt of a differential equation, then the existence and uniqueness theorem of differential equations, the study, states that this is the only solution. You don't have to keep looking for other ones. Once you find it, that's it. All right, so by hook or by crook, if you can find the unknown solution, or you can find the solution to the differential equation, then that is the only solution. And there's a special theorem in differential equations called the existence and uniqueness theorem. All right, so the big question that we have is, all right, well, we have this this differential equation, can we actually solve it? That's the central question here. So, and what would the answer to it be? All right, and so so the big question is, right now, we care about this differential equation. So, question is there a solution? X of t for this differential equation. And the answer is, you ask the mathematics department this, and they say, yes, there is. It is x of t is equal to capital X, which we call an amplitude, times the cosine of omega t. So capital X is called the amplitude, as a constant. There's no time dependence in the amplitude. So we have a constant amplitude. And omega, again, we have to reuse Greek variables or Greek letters. So we saw omega as what was called the angular velocity back in kinematics. This is different. This is called the angular frequency. It's given in terms of radians per second, just like the angular velocity, but it's totally different. Okay, so this is called the angular frequency. Now, inside the cosine function, at the end, I know we sometimes use degrees in there, but we really, the most natural variable or the most natural measure inside the argument of a cosine function is radians. Well, we know that this time is in seconds. In order to have the argument of the cosine function be radians, then you have to have omega being radians per second. So what does this mean? So again, let's rewrite this solution. Let's just kind of rewrite everything here. Let's put everything together. So I have, in general, the differential equation of the mass in the spring. I know that it looks like this. The second derivative of x as a function of time plus k over m times x as a function of time equals 0. Okay, so we have this complicated differential equation. And I asked the math department, hey, is there an answer? Yes, there is. X as a function of time is capital X cosine of omega t. All right, what's that look like? So I'm going to have my time axis, and let's say at time 0, the cosine of 0 means the cosine of 0. This is my little x-axis. Cosine of 0 means that I'm going to have amplitude capital X. Capital X times the cosine of 0. Cosine of 0 is 1, so it's going to start with capital X. And what's going to happen? What's the cosine look like? Well, the cosine is going to go from -1 to 1, but it's actually going to go from, the whole function is going to go from cap X to negative cap X. If the cosine goes from -1 to 1, I'm going to multiply it by capital X. I scaled it to go from capital X to negative capital X. So this thing is going to go back and forth forever. It's going to cut like a cosine. Come through 0 to negative X, back to 0, so on and so forth. It's going to do this forever. All right, hopefully I drew this well. So it looks like it's a cosine wave, right? It looks like a wave. All right, and so we look at this and we say, well, now let's understand what this is, though, right? What are we actually doing here? Let's understand what this actually means. Remember, I'm looking at a mass on a spring. So I'm going to declare, let me draw this bigger, I guess. I'm going to declare the equilibrium position as 0. This is my x-axis. All right. So initially I'm in compression. Well, we'll say initially, well, let's not worry about that. Let's just say initially I'm stretched. A little different than what I said before. Initially I'm stretched out. How far? Stretched out by capital X. Okay, so initially at time 0, the system is stretched out as far as it can go. I let it go. What's it going to do? It's going to go down to 0. Then it's going to go through 0 and go all the way to negative capital X. All right, go to negative capital X, comes back through 0, back to positive capital X, back through 0, back to negative capital X, back and forth, back and forth, back and forth, forever. Again, this is called simple harmonic. Harmonic means periodic, back and forth, motion. It's going to go back and forth forever based upon this cosine function. And again, this omega is in radians per second. This essentially it is, one entire revolution is 2 pi radians throughout, the cosine is a circular function. So a lot of nomenclature between what we're talking about with rotational motion and oscillation. So it's a little bit unfortunate because they're very different. But again, at the end of the day, a trigonometric function is officially called a circular function. If you look up circular functions, let's say in Google, you will find sine, cosine, and tangent. All right. So what does this actually mean? So again, this is what we're modeling here. So we got it. We understand it. Let's understand what this radians per second business is. All right. So if you look at a sine function, well, let's look at the cosine function first, I guess. cosine of theta, for instance. All right. So when I look at that, well, I got done writing what it looks like here, in a linear graph that you're used to. Again, if I'm just looking at the cosine, I'm going to go from 0 to 1, back to 0, and on and on. And what's this going to be? Well, let's just say this is theta, right? And it's going to start off at 0. It's going to go through 0 at what? Well, it's going to start at 1. It's going to go 0 at basically pi over 2 radians. And it's going to be -1 at what? Pi radians, 180 degrees. Back to 0 at 3 pi over 2, and then back to its maximum value at 2 pi. So let's go through 2 pi radians. Every single cycle, as we call it. So it's going to go, so the function goes through the cosine of theta goes through 2 pi radians per cycle. When I say cycle, I mean it's a full compression to going through 0 to full stretch, back to 0, back to full compression. So if I take it and I figure out, a cycle is basically I look at it at some instant and basically going all the way out and coming back to its original position where I looked at it. That's called a cycle. I can pick anywhere on the function to say I'm going to start my cycle. And basically, a cycle is the object going through its entire motion and coming back to where you originally started. That's called a cycle. So going through a cycle is 2 pi radians. So essentially, if theta equals omega t, it's going to, omega is really how many radians per second. That's the angular frequency. Okay, so essentially, it's basically, how many radians per second. It is a rate at which the function is going. So we can use a lot of angular terminology that we saw before. So we happen to know, well, if I'm counting how many of these cycles, I could say, well, I know that, if I know there's omega, radians per second, I know that there's 2 pi radians in a cycle. I could say the following. I could say, well, I want to find cycles per second, right? So I know I have omega is 2 pi radians per second. And I know that one cycle, so F cycles can happen at, basically F cycles or cycles per 2 pi radians. So I can figure out a frequency of counting by saying that how many cycles per second is basically, it's omega divided by 2 pi. Or I can say that omega is 2 pi F. All right, so F is your ordinary frequency. All right, so let me erase this. F is the ordinary frequency. So again, if I know that there's omega is 2 pi radians per second, I want to figure out how many cycles. Well, literally, I divide by 2 pi. So it's omega divided by 2 pi. That gives me cycles per second. We have a special name in physics that we give to this quantity. We call this the Hertz. Named after the great German physicist Heinrich Hertz. So I'll talk, and if anybody takes physics 2 from me, I'll talk a little bit about Heinrich Hertz. It's extremely important, particularly for electromagnetic theory, electromagnetic waves. So we honor Heinrich Hertz with we usually call Hz, with cycles per second is if I'm just counting how many cycles per unit time. One goes through, okay, there's 1. Another one, or there's 2. Another one, okay, there's 3. And I just count how many times. So let's say I'm counting crests. I want to figure out how many times, how many crests happen per unit time. I just count them. There's 1, there's 2, there's 3. This is basically number of cycles per unit time. Each cycle corresponds to 2 pi radians. So if I want the amount of radians per unit time, then that's omega. If I want the number of cycles per unit time, I divide out the number of radians in a cycle, 2 pi radians in a cycle, and now I get cycles per second. If I want to figure out how long a cycle is, that's called the period. So the period is the time duration of a cycle. For some reason in physics, we call this usually a capital T for period. I guess it's capital T stands for time. All right, so we use period, capital T usually, and that's given by a simple equation. It's 1 divided by F. 1 divided by F. If I know the cycles per second, I can figure out how long a cycle takes, called the period, by taking 1 divided by F, or if I go to the original equation, it'd be 2 pi divided by omega. That's another way of expressing it. 2 pi divided by omega. So 2 ways of expressing the period. Now, what's interesting is when we talk about waves, we're going to reuse a lot of this terminology. But not to get confused, this terminology is what? This terminology is talking about periodic repetitive motion of a mass going back and forth in a periodic repetitive way. And so it has sinusoid or basically a cosine function in its motion, and it has a lot of the behavior. If I graph, basically where it is with respect to time, it looks like a cosine wave or a sine wave. So again, it looks like our perfect idealized wave. Now that we would say, if I were to say, hey, draw a wave, you would draw something that looks like this. And this turns out that is the functional form of the position with respect to time for a mass on a spring. Okay? And so we would say the length of time is the period. All right, and so that's very important nomenclature. All right, and so let's kind of go back and now one of the questions you might want to ask is, okay, well, I can believe that that this is the functional form of the mass of the spring, but can you prove that? Because physics is all about proving things. Okay, so when someone throws you a function, one of the first things you want to do is actually prove that it is true. All right, so how do you do that? Well, you take this form and you figure out a way to substitute it into the main differential equation and prove that it truly is the solution. So let's do that. In physics, everything must be proved. Okay, everything is derived at logic and proof, and essentially that's why I'm showing you this, because the book just magically gives you this function, but there's nothing magical in physics. Everything has a rational expression. All right, and so for me, how do I do this? Well, I need to get the second derivative with respect to time. So if you don't understand what I'm doing, that's okay. I want to get the main notion out of it. So again, in calculus, you would say, oh well, v of t is the time rate of change of the position, which means I need to take the time rate of change of the function for the position. Constant capital X, cosine of omega t. Constant doesn't get operated on by a time rate of change, but anybody who's had calculus 1 knows that the derivative of a cosine is a negative sign. So a negative sign, a negative SIGN comes out. And I have negative capital X sine of omega t. That's the SINE sign. And in calculus, you have what's called the chain rule. If you have a function inside of a function, you take the derivative of the outer function first, and you keep digging in delving or burrowing into the function and multiplying factors for every single derivative of internal functions. So here's a composite function. It's a function omega t inside of a function cosine. So I have to now take what's called the derivative of omega t, and derivative of that slope of omega t is just omega. So that has to be multiplied out front. So there's an additional omega out front. So the answer is negative omega cap x sine of omega t. That's the velocity. Again, I would write this in my notes that is how you figure out the velocity. The position of a mass in a spring is x of t is capital X, which is the amplitude, cosine omega t. The velocity is negative omega out front times capital X sine of omega t. But I really want the acceleration, right? So I really want to go one more. So A as a function of time is the time rate of change of, well, it's actually, you can think of this as, let's see, am I on the camera yet? But you can think of this as the second order time derivative of the position, which, by the way, is the first time derivative of the velocity. So I got to do d by dt on this functional form, negative omega, capital X, sine of omega t. Again, x is a constant. Actually, in this particular problem, omega is a constant too. So they don't get operated on. Again, if anybody said calculus 1 knows that the derivative of a sine is a cosine. All right, and so again, by the chain rule, another omega pops out. So I find out that A of t, let's see if I can write this, A of t is equal to, how low I can go here. A of t, yep, I'm still there, good, is equal to negative omega squared, capital X, cosine of omega t. All right, and again, that would be your functional form for the acceleration. All right, so again, A is a function of time. I'll write it up here, so I think there's a little glare. A is a function of time is negative omega squared, amplitude times the cosine of omega t. And in fact, if I look at this, hey, capital X cosine omega t is exactly the position. So I could hypothetically write this, that A of t is negative omega squared little x of t. That's another way I can write this as well. So again, these are nice functions to write down. They're very important. Now, how do I use this function now? Well, I will substitute it into the original differential equation. So I'm going to remember this. Let's erase the rest of this stuff. And again, I'm proving that this is the actual solution. And I take nothing for granted here. I prove everything. And so I'm going to substitute it here. So instead of this second order time derivative, I'm going to put down what it actually is. Negative omega squared, cap x, cosine of omega t, plus this term, k over m. Cap x, cosine of omega t equals 0. I just rewrote the equation, but I substituted for that first term with this expression. All right, so again, this really is, if I really want to be explicit here, this is really the second time derivative respect to time, and that's A of t. Okay, I'm just doing, I'm performing the appropriate calculus, and I am just performing a substitution. So let's look at this. We have an equation. We have stuff that's common. We have capital X on both sides. We have cosine on both sides. I can cancel them out. So this is a solution, provided what? That negative omega squared plus K over M equals 0, or omega equals the square root of K over M. I'm going to be explicit here and call this omega naught. And I'm going to call it omega naught for a reason, because I want to call this, and this will become more clear later, I want to call this a natural frequency. Of simple harmonic oscillator. That's what this is. This mass on a spring, or we can call it the mass on a spring with no friction, basically. But we generally refer to this as a simple harmonic oscillator. And again, it has to be the mass on the spring. You know what? Let me be more specific. The harmonic oscillator would be more general. This is particularly the mass in the spring. Natural frequency of mass on a spring. Now let's take a look at this. This is telling me that because a system has certain characteristics, has a spring constant K and a mass M, it naturally wants to oscillate at a frequency K square root of K over M, a frequency entirely dependent on its characteristics. That's the frequency it likes the best. And naturally, that's why it's called a natural frequency. The system naturally wants to oscillate at that frequency. Left to its own devices, if you pulled on that mass, and if you kind of saw this maybe in the mass in the spring lab, that if we had to go set the damping coefficient very high to get the spring to stop going back and forth. But if you're to pull on the mass, you're going to notice that it would go up and down. Up and down. That's what it's going to do. So again, and it's going to go up and down at an oscillation frequency of what? This, the square root of K over M. All right. That is the natural frequency of the simple harmonic oscillator. So that is requirement. If this is the solution, if x of t is cap x cosine omega t, the requirement is that omega must be the natural frequency and it must be equal to square root of K over M. That's very interesting how an object, a system, wants to oscillate at a natural frequency based upon its characteristics. In this particular case, the spring constant of the spring and the mass M. These are characteristics that define a particular mass in a spring system. Okay? We can also kind of look and say, okay, well, I know the omega naught is square root of K over M. Can I write it in terms of the other variables? Yeah, I can say that, but what, again, this is in radians per second. It's angular frequency in radians per second. So let me kind of rewrite this. So again, I'm looking at my mass in the spring. I'll keep the original differential equation up. So we've proven it, that is the solution, provided that caveat. So again, the angular frequency of the mass in the spring is the square root of K over M. Again, all of this that I'm writing is only for the mass on the spring. Okay? Mass in a spring system, not just any general oscillator. This is one mass on one spring. Now, again, what did I say? Omega is 2 pi f, so I can say that f, the ordinate is, again, this is in radians, this is angular frequency in radians per second. If I want the ordinary frequency, again, it's omega over 2 pi, or 1 over 2 pi. Square root K over M, frequency in hertz. I want the period. It's just 1 over f, right? So it's 2 pi square root M over K. Period. All of these are for a mass. Everything I've written on this board is entirely for the mass on a spring. Nothing else. This is a differential equation that governs it by the application of Newton's second law. This is the natural frequency. And if I really want to be real about this, I put little zeros at the end. F naught is the ordinary frequency. T naught is the period. So I know a lot about my system without really doing anything. I mean, if you tell me the mass and the mass and the spring constant, I can tell you all of this right off the bat. Okay, these are characteristics of the system. All right, let me do a few problems here. Wrote a lot of theory here, so let's actually work out some problems before I go too far. All right, kind of go back to the basics here. All right, so I'm gonna work some problems now. Your book does oscillations in chapter 10. The previous book, the OpenStax, actually waited till the end of the first semester and did it toward the end. So the OpenStax did it in chapter 16. All right, so it's gonna we're gonna be a little bit out of whack as far as chapter numbers for this chapter. So OpenStax chapter 16 was oscillations. So we're gonna do a problem in OpenStax 16.1. All right, so again, we're on chapter 10 in our book. All right, so the answer, the question is, fish are hung on a spring scale to determine their mass. A, what is the force constant of the spring? In such a scale. If the spring stretches. .00 centimeters. For a 10.0 kilogram load. All right, that's A. B, what is the mass of the fish, of the fish that stretches a spring .50 centimeters? C, how far apart are the half kilogram marks on the scale? Okay, so here we go. Fish are hung on a spring scale to determine their mass. What is the force constant of the spring in such a scale? If the spring stretches 8.00 centimeters, for a 10.0 kilogram load? B, what is the mass of the fish that stretches the spring 5.50 centimeters? C, how far apart are the half kilogram marks in the scale? All right, so how do we do this? Well, again, this is an application. This kind of goes back to kind of reviewing Hooke's law a little bit to remind ourselves how it works. So this is a little bit of a review problem, but again, we're trying to develop this generalized concept of oscillations. And so for part A, what do we know? So again, this is 16.1 open stacks, 16.1, and I'm going to now do A. All right, so I'm going to do A. All right. The mass is hung on a spring. So again, let's kind of look at, draw a little picture. I have let's see here. Let's say I'm at equilibrium. Let's say I don't have any mass on this spring at all. The spring has a spring constant K. Now I want to apply a mass and see how much it stretches. So again, this is the equilibrium. Very much like our Hooke's law lab that we had recently. All right, now I'm going to hang a mass. What's that going to do? Well, I'm going to hang the mass now. Same spring. And I'm going to hang some sort of a mass, and this is equilibrium. Situation. And I noticed that the mass is going to stretch. Here's the original location, and it stretches by an amount what? It stretches by an amount y. Okay, that's the displacement of the mass. It stretches by an amount y. All right, so what do we know about Hooke's law? Well, we know that there's going to be, first of all, there's going to be a weight, mg. It's going to pull down. It's going to be, and if this is an equilibrium, a new equilibrium, which is hanging, that means it's going to be met by an equal and opposite force, and that would be Hooke's law. That would be given by Ky. So if I apply Newton's second law in the y direction, sum of all forces in the y direction is going to be what? Ky is up minus mg, and if it's hanging motionless, it's in a new equilibrium. There's no acceleration. It means the right-hand side of Newton's second law is 0. All right? And so I know m, I'm being told what m is, and I also know what y is. So I can basically, I measure y, or I'm being told in this problem, but I'm looking for k. So I'll essentially say, well, ky is equal to mg, divide both sides by y, get the k is mg divided by y. And let's see what that would be. Well, I'm told that the mass, my givens, the mass is 10 kilograms. G is 9.80 meters per second squared. And y, I'm told it's gonna stretch 8 centimeters, or of course we put that in SI, so 0.0800 meters. And if I do that, I figure out empirically what the spring constant of the spring is. That's a characteristic of the spring. It'd be 1,225 newtons per meter. And that's how you figure out. Someone hands you a spring and says, I want you to determine what the spring constant is, the force constant. What do? You go and find some little hook, you hang it, and then you figure out a mass that you know, put the mass on there and figure how much it stretches. And you do this formulation. That's all you have to do, and you can report back what the spring constant of the spring. It's a simple, very simple experiment. Very simple measurement. Now we know what the spring constant is. At that point, we can now determine what unknown masses are. Or, or if we have a mass, we know how far it's going to stretch. We now know a property of the spring. All right, so we can kind of keep, so again, I'm going to just kind of erase everything. I'm going to keep track of this number. We're going to do part B now. All right, so I know my spring. Spring in this problem has a force constant or spring constant 1,225 newtons per meter. Okay, I'm just going to put that in the parking lot. And let's now do part B. All right, so let's remind ourselves what B says again. B wants, says, what is the mass of the fish that stretches the spring 5.50 centimeters? Oh, okay, so what was our equation again? We said that we did Newton's second law in the y direction. What did we say? We said that Ky is mg, right? So again, look back at part A. That's from Newton's second law in the y direction. We can reuse that, but now we're looking at something else. We now know what the we now know what the stretch is. We want to now, and of course we know K because that's a characteristic of the spring. That's going to be true in any future calculations in this problem. And so what we want to do is solve for M. So solve this equation for an unknown mass now. I did it for a known mass. Now I can figure out, what any unknown mass is. Now that I know what K is, I can determine any unknown mass by basically measuring the stretch. So solve for it, Ky over G. So the mass is going to be the 1,225 newtons per meter again. Y this time, well, we're told it stretches 5.5 centimeters, but of course we want to use meters in SI, so 5.50 times 10 to the negative 2 meters, and G, 9.80 meters per second squared. When I do that calculation, I find out that that unknown mass that stretches it like this is 6.88 kilograms. Great, I can now use this spring to essentially a mass meter. I can make my own scale. I can hang whatever mass I want on it now, and I can figure out what those masses are. Now that I did that original experiment, figure out what my spring constant is, I can now use it essentially as a scale for me to determine any unknown mass. All right, the last part is very interesting. We now want to actually make a scale, and we want to actually figure out what they have, how far apart would the half kilogram increments be. So we're gonna make ourselves a little scale. All right. So we got this. That was just the part B. I don't need the answer to part B anymore. So we want to figure out the half kilogram. So it says how far apart are the half kilogram marks on the scale. So we want to make ourselves a scale. Well, let's just let I don't know Y1. I'm sorry. Let M1 for instance be a half a kilogram. Let's pick a half a kilogram. So what Y1 corresponds to that? What Y1 corresponds to a half a kilogram? What stretch? Well, what do we know? Again, Ky equals mg for our little equilibrium scale equation. And I know in M I want to get a y, so it's a linear relationship. Why? Because K, we're going to get what? We're going to get M over K. Oops, I'm sorry. G over K times M. We're going to kind of have a slope equation, a linear equation, and G over K will be the slope. And so in general, I can solve for that. So I want to find a Y1 for a given M1. Okay, well, that would be 9.80 meters per second squared times 1,225 newtons per meter, and then what? Multiplied by M1, which in this case is a half a kilogram. And if I do that, I find out that y1 is going to be 4.0 times 10 negative 3 meters, or 4.0 millimeters. All right, so that means that on my scale, y1 would be a 4.0 millimeters. So I'd put half kilogram, and basically I'd figure out where 4.0 millimeters was, and I'd stick a little hash mark there that and maybe a label that represents 0.5 kilograms. Now the question is, well, where would I put the next half? I'm going to go half integral or half kilogram increments. So that's a half a kilogram. Well, another half kilogram is 1. I'm going to go half a kilogram more to go to 1 kilogram and figure out what that is. So I'll call that y2. G over K, my constant, times M2. M2 is going to be 1 kilogram. So let's see, that's again 9.80 meters per second squared, divided by 1,225 newtons per meter, now times 1 kilogram. I will find out that that is going to be 8.0 times 10 negative 3 meters. Or 8.0 millimeters. So to go from a half integral or half kilogram increments, well, my scale would do what? I mean, I would come down here at about 4.0 millimeters, and I say, well, that is a half a kilogram. And I measure closely and say, okay, here's 8.0 millimeters. Well, that would be 1.0 kilograms. So my increments, my change increments is what? It's a half a kilogram, or it's 4 millimeters, which is the answer to my problem. It says how far apart are the marks for every half kilogram increments. Well, the answer to that would be, well, I did it for a half a kilogram, that's 4.0 millimeters. I did it for 1 kilogram, they're half a kilogram more, that's 8.0 millimeters. Well, what's the difference between the two? 4.0 millimeters. So I could then say, okay, well, that's the case. So it's linear. So I can put, okay, 12, 16, I can keep going on for every half kilogram increment. I now know how to make my scale. So not only can I make a scale, I mean, I can actually make a calibrated scale. Okay. All right, I'm going to do another problem. I'm going to go to OpenStack 16.3. All right, let's see what this is. One type of BB gun uses a spring-driven plunger. To blow the BB from the barrel. A. Calculate the force constant on the plunger's. Oops. Calculate the force constant . the plunger spring. If it must compress it 0.150 meters, to drive the 0.0500 kilogram plunger to a top speed of 20.0 meters per second. And then B, what force must be exerted to compress the spring? Okay, so OpenStack 16.3. One type of BB gun uses a spring-driven plunger to blow the BB from the barrel. A, calculate the force constant on the plunger spring. If it must compress at 0.150 meters to drive the 0.0500 kilogram plunger to a top speed of 20.0 meters per second. B, what force must be exerted to compress the spring? Okay, so we have a mass in the spring type problem, and we want to find out, number one, what is the spring constant? So let's kind of convert this into English. Okay, now what I'm going to do is I actually want to use this as I'm going to do an energy calculation to do this. This is early on where we were talking about energy conservation. So I actually want to employ the conservation of energy to this problem. Okay, so the initial situation, I'll call this the before and after. All right, before the spring is entirely compressed. All right, so spring fully compressed. All right, so what we have here is a fully compressed situation, and the mass, this is the plunger, is in the barrel of the BB gun, right? And so initially, what do we know? Well, we know the kinetic energy initial is 0. The potential energy, well, it's compressed by an amount 1/2 kx squared, and we're told that x is 0.150 meters. Fully compressed. Well, the total energy, total mechanical energy, is always the sum of the kinetic energy plus potential energy. But the kinetic energy, the plunger is initially at 0. So that means that the total energy of the system is going to be 1/2 kx squared. Everything is potential energy initially. Now what's going to happen? Well, you're going to release, you're going to pull the trigger, and the spring is going to entirely unfurl, and it's going to go to its full length, and then as it unfurls, it's going to shoot this plunger out all the way. It's going to decompress by an amount X, and all the potential energy that's coiled up and stored up will then become kinetic energy. So the after plunger at top speed. So the spring is entirely compressed. Again, this spring has a spring constant K. So what happens now is the total energy. Well, let's see here. Now, potential energy, there is no more stored energy in the spring. It's released it all to the kinetic energy. So potential energy final is 0 now. The kinetic energy final is 1/2 mass of the plunger, final velocity of the plunger squared. So if you want to, again, at any given time, the conservation of energy applies. The total mechanical energy is always the sum of the kinetic and potential. So in this case, the total mechanical energy, right, when the plunger is being shot out, is going to be 1/2 mv squared. Again, m is the mass of the plunger. Okay. All right. So what happens there is I can employ the conservation of energy and say that the total energy must always be the same. That means that 1/2 kx squared must equal 1/2 mv squared. In a given time, the total energy of the system must add up to the same quantity, the same total energy. Turns out, and initially, there's only potential energy, no kinetic energy. At the time the plunger is shot or released, after the spring is fully decompressed, there's no potential energy anymore. Now it's all kinetic energy. But the two must equal the same value, same total value, so I can equate these two. Okay, now what's left is all I have to do now is solve this algebra problem. So I'm going to erase all this, give myself some space. And the easy thing is I can just cancel out these halves. And I want to solve for K. K is mv squared over x squared. And I know everything. K, the mass of the plunger, is going to be 0.0500 kilograms. Hold that in a given. The final speed, top speed, 20 meters per second. I was told that in a given. Divide. Full compression, 0.150 meters squared. Don't forget to square these. And if you do all this, you find out that the spring constant, again, another way to determine the spring constant, 889, very strong, newtons per meter. It's a very stiff spring. That is the constant that is characteristic of the spring in this particular gun. Now that I know the spring constant, I can determine a lot of things. So part B just says, hey, what force did it take for me to compress that spring in the first place? Well, now I know the spring constant. Part B is a one-line calculation at that point. What's the force to get that compression? F equals kx, right? If I compress by an amount x, the force that I had to apply to basically counter Hooke's law is going to be kx. I know k now. So for full compression, 889 newtons per meter times 0.150 meters, the first compression. That force required for me to do that will be 133 newtons, and a pretty good force. A lot of energy sort of in that BB gun. All right. Okay, do another problem. I'm going to do open stacks 16.7. That says, what's the period? Of 60.0 hertz electrical power, like you have in your wall. Well, what do they tell us? They told us F, 60.0 hertz. That's our given. How do you figure out the period if you know F? Very simple. T equals 1 over F. 1 divided by 60.0 hertz. So hertz, remember, is a per second. Period will then be in seconds. And if I do that, I get 16.7 or 0.0167 seconds. Or I can multiply that by 1,000 and get, say, 16.7 milliseconds. That's my period. Okay. All right. So moving on. Another problem. I'll do OpenStack 16.8. That says if your heart rate is 150 beats per minute. During strenuous exercise. Again, one thing I say about OpenStack is it's very, very medical affiliated. I mean, they really want to train future doctors and stuff. So, and that's another good thing about this book. So they give a lot of medical examples, and I try to repeat those for you. Strenuous exercise. What is the time per beat in units of seconds? Okay, so if your heart rate is 150 beats per minute during strenuous exercise, what is the time per beat in units of seconds? All right, so how do we do this? Well, what are we being told? Well, we have to do a little conversions here, so I'm going to erase all this. And so we're told a frequency, beats per minute, basically. That's basically cycles per minute, right? Your heart's constantly going through a cycle. So your frequency is going to be 150 beats per minute. But you don't want to do things in minutes. You want to do things in seconds. So we got to convert that. So 1 minute has 60 seconds. So a better way of doing my frequency would be 2.5 beats per second. Probably call that a 2.5 hertz, if you will. Every heartbeat is a cycle, max min, either your diastolic, systolic blood pressure and everything. It's one cycle of your blood pumping in your heart chambers. All right. So now what do we know? Well, we're asked basically what's the time per beat. So we need to get the period. So period is 1 over F, or 1 over 2.5 beats per second. And we'll find out that the period is 0.4 seconds per beat. That's the answer. T, each heartbeat when a person's in strenuous exercise, 0.4 seconds per beat. All right. Let's do some more problems. Talk about actual oscillations now. So I want to do open stacks. 16.13. Okay, this says a type of cuckoo clock keeps time by having a mass bouncing on a spring. Usually something cute. Like a cherub. In a chair. What force constant is needed? To produce a period of 0.500 seconds. Or a 0.150 kilogram mass. All right, so again, a type of cuckoo clock keeps time by having a mass bouncing on a spring, usually something cute, like a cherub in a chair. What force constant is needed to produce a period of 0.500 seconds for a 0.150 kilogram mass? All right, so again, we're going into oscillatory motion now. So let's put this into English. All right, so we derived some equations, and so let's start using them. So again, our givens, we're looking for the force constant, K. We don't know what that is. We know the period of this clock is going to be 0.500 seconds. We also know the mass of the little cherub, and that's going to be 0.0150 kilograms. And so we know there's a formula for a period. Again, this is for a mass on a spring, and this is what we have. So formula for the period is 2 pi square root m over k. This is for a mass on a spring, period for mass on a spring. Again, this equation is specific for a mass on a spring. Which is exactly what this is. We want to get K. So let's kind of rewrite, it's going to flip the equation over here. So I can write this as a square root of m over k is what? T over 2 pi. All right, let's turn the equation upside down to get k on top. So square root of k over m is 2 pi divided by t. Let's square both sides. K over m is 4 pi squared over t squared. And then one more line of algebra. I need to cross multiply to get m, so I'll give that k. I'll write this up here. K is equal to 4 pi squared m divided by t squared. Okay, I've now solved for k. All right, now what do I do? Well, I put numbers in, just like I always do when I show my work. 4 pi squared, what's the mass? 0.0150 kilograms. And the period squared, I have 0.500 seconds squared. I find out that my spring constant for this clock is 2.37 newtons per meter. All right, so I was able to use I was able to study the oscillatory motion and figure out the spring constant from watching the oscillations. Another way of figuring out the spring constant. There's many different ways of figuring out the spring constant. All right, let's look at another question. Okay, erasing this stuff, do another problem with OpenStax. Okay, so OpenStax 16.14. That says what? If a spring constant of a simple harmonic oscillator is doubled, by what factor will the mass of the system need to change? In order for the frequency of the motion to remain the same. All right, so if a spring constant of a simple harmonic oscillator is doubled, by what factor will the mass of the system need to change in order for the frequency of the motion to remain the same? Actually, I missed a word. To remain the same. Sorry about that. Okay, so let's put that in English. So I have a simple harmonic oscillator, mass in a spring. And I'm just going to say I have a, let's say the mass is m and the spring is spring constant is k. So general, we're just going to do, this is basically a theoretical problem. So if I have so let's say for instance, that I know I have a spring, I'll call it spring 1, has mass 1 and K1. Those are the two characteristics of my spring. So what's my frequency? Well, I look up my formula here for frequency of a mass in a spring, and as if you look at it, you say, well, that's going to be 1/2 pi square root of K1 over M1. Again, it's 1/2 pi square root of K over M. In this particular case, it's K1 and M1. Now, let's say I have a spring 2. Well, it'll be defined by an M2 and a K2. And the frequency, which I'm being told needs to stay the same, I'll keep F the same. Again, that would be 1/2 pi square root of K2 over M2. I'm being told the frequency must be the same. That means that these two can be equated. So 1/2 pi square root of K1 over M, sorry, K1 over M1 has got to equal 1/2 pi the square root of K2 over M2. The two are equal. I can cancel out the 1/2 pi's. And I'll square both sides. And I'll find out that I have that K1 over M1 is K2 over M2. Okay, squaring both sides. Now, let's see, what do I know? Well, let's see, I know that K2 is 2K1. Right? I'm told that I'm doubling the spring constant. That's what I'm told in the problem. Won't put that up there. So plugging this in, I get K1 over M1 is 2K1 over M2. K1's cancel. If I do the algebra, what do I find out? I find out that M2 is 2M1. If I double, to keep the frequency the same, if I double the spring constant, I better double the mass too. Okay, so the mass has to be also doubled. All right then. So what we're gonna do now is talk about another formulation. Take a swig of my water real quick. Okay, so this is not the only spring constant in I'm sorry, this is not the only simple harmonic oscillator in town. I've been very careful to refer to, instead of a generalized simple harmonic oscillator, I've been very careful to particularly refer to a mass and a spring. Well, let's talk about another behavior. So let's talk about what's called the simple pendulum. So a simple pendulum is one. So basically a pendulum is something that essentially goes back and forth off of a pivot. But the simple pendulum is the following. So essentially all the mass is in a pendulum bob. So let's imagine I have a support and I just have a string with a bob at the end. The string has a length L. Okay, so say I have a bob, and I'm going to say the string is massless. So all mass, this is what makes it a simple pendulum. No mass anywhere except at the bob. All mass is located in bob. Okay, now this is just going to hang down at an equilibrium position. naturally. Okay, now I could actually refer to this situation as a zero potential energy. So I'm going to say that at this point, I can declare this where the bob is at this level. I can call this the zero of potential energy. Now let's take this bob and let's angle it up a little bit. Let's just kind of let's set it. So I'm going to stick the bob right here. So I'm going to take this pendulum. I actually want to, if I know from experience that if I were to take a pendulum like this and let it go, it's going to be like a hypnotist watch. It's going to go back and forth, back and forth, back and forth, right? Just like, like you have the classic hypnotist. All right, so let's imagine that I'm going to hold the pendulum up, and there's going to be an angle theta right here. All right, I'm going to hold the pendulum up, and the pendulum is going to have a height h, let's say. And I know that the pendulum is always going to have a weight mg. So there's going to be a gravitational potential energy mgh. It's going to have a maximum gravitational potential energy, no kinetic energy. I'll let go. So again, at this location, potential energy equals mgh. Kinetic energy is 0. Okay, I'm holding it. I'm going to let the pendulum go. It's going to swing down, lose potential energy. By the time it gets down to the bottom, it'll be at the 0 potential energy. It'll have maximum kinetic energy. It'll be back in this equilibrium position again. But again, just like the mass in the spring, it's going to be at its maximum kinetic energy. It's going to blow right through equilibrium. It's going to go all the way back up, and it's going to temporarily come to rest, in a symmetrical way right here, again, at a height h. It'll temporarily come to a stop, have all gravitational potential energy mgh, 0 kinetic energy. It'll swing back down. It'll be at the 0. It'll be straight down vertically. It'll have 0 potential energy. It'll be at the 0 potential energy. It'll have maximum kinetic energy, and it'll go right back up to where it started again. 0 potential energy, temporarily stop. Potential energy mgh temporarily stops. So it'll be a kinetic energy of 0, and it's just going to go back and forth over and over again, a simple harmonic motion. It's gonna essentially go in a motion that's going to be periodic, back and forth, and if there's no friction in my system, it's going to do it forever. Okay. Now, again, I gave you an energetic argument for this. Can I give you an argument using Newton's second law? Well, let's see. Let me erase some of this, and let's try to give an argument with Newton's second law. Okay, so what I like to do here is I like to work in polar coordinates. Why do I want to do that? Because there's a circular symmetry. This thing's going, this basically tracing out a part of a circle. Circular symmetry is the best. So I'm going to work in polar coordinates. And it'll be, in this case, r theta. But again, I'm going to be looking at the tangential. So again, there's going to be a radial component. So I kind of look at the bob. There'll be a radial axis, radial component, and the other component. And again, any right-handed coordinate, any orthogonal coordinate system is going to be at right angles for a particle. It's x, y, z, or in this case, the radial and the tangential are at right angles. So again, this is mg, hypotenuse. I am giving the coordinates in terms of, and again, the components are in terms of the coordinates that I'm choosing. This is the tangential component. This is the radial component. I don't expect there to be any kind of motion in the radial direction. The only direct motion is going to be the tangential. And so there's going to be, if I mean, again, I can always write that the sum of all forces, this is Newton's second law, sum of all forces in a general vector equation is mass times acceleration. Again, when I write a general vector equation, it is agnostic to any coordinate system. Once I choose a coordinate system, I can write in terms of x, y, z, or I can write in terms of r theta. Once I choose a coordinate system, then once I've committed to a coordinate system, then I write Newton's second law for each coordinate. Well, I don't care what's going on in the radial direction. What I care about is the tangential direction. So I really want to particularly focus on the sum of all forces in the tangential direction is mass times acceleration in tangential direction. Again, little t means tangential. Well, let's see, sum of all forces. Well, forces on this object would be tension going entirely along the radial. Well, that's not going to be in the tangential. The only force that's going to operate in a tangential is the component of the weight. And if I look at geometry, if this angle is theta, this angle is also theta. And opposite the angle is mg sine of theta. So the left-hand side, and it's going to be going toward the left, is negative mg sine of theta is equal to, I'm just going to drop the tangential, ma. I'll call it ma tangential. All right, and so that is going to be the equation of motion for the tangential direction. Now, the problem is what I actually have here is that I actually have, the way it's written, I have a nonlinear differential equation. So those are very hard to solve. Okay, so I have to figure a good way of solving this, or at least approximating, because a nonlinear differential equation is very, very hard. What makes it nonlinear? Because theta is a function of time. I have sine, which is completely nonlinear. That's a transcendental function, and I have this function of time inside of sine. So it's a complicated looking equation. So I need to make an approximation at this point. So I'm going to do what's called, I'm going to linearize the equation. I'm going to linearize, it's actually a word, the differential equation. How do I do that? Well, if I were to tell you, or coming in this class, I were to say, hey, define the sine function, define the cosine function. You might say, oh, well, that's sine is opposite of hypotenuse and cosine is opposite adjacent of hypotenuse, right? Well, that's actually not the definition. That's actually a geometrical application. It turns out that the sine and the cosine are defined by infinite series. All right, and so what I can do is the actual sine function, let's say I say sine of theta. The sine of theta is an infinite series. It's actually defined as theta theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus theta to the 9th over 9 factorial minus so on and so forth, going forever. Now, factorial is a special way of saying if I take n factorial, that exclamation mark is not me saying n really loud. It's me saying n factorial. This is the same as n. What I would pronounce as n factorial. All right, and how you figure that out in general is I just start multiplying. I take n times n minus 1 times n minus 2. I keep going all the way down until I get like 3 times 2 times 1. And I get this big number. In fact, a factorial is a very fast growing function. So what would 3 factorial be, for instance? Well, 3 factorial, I follow my script. 3 factorial would be what? Let's see, 3 times 2 times 1 is 6. 5 factorial, what would that be? 5 factorial, 5 times 4 times 3 times 2 times 1. So that would be 5 times 4 is 20, times 3 is 60, times 2 is 120. 5 factorial is 120. If you were to plug in something like 30 factorial in your calculator, it would blow up. It would be such a large number. I think 50 factorial, I don't think your calculator can even hold that number. So again, you blow up real fast. 3 factorial is 6. 5 factorial is already 120. So actually, you're dividing by larger and larger numbers, so that makes each of these following terms less and less important. So when your calculator does sine function, it's actually doing this series for you. Cosine is also an infinite series. Cosine of theta would be defined as, for instance, 1 minus the evens, theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial plus theta to the 8th over 8 factorial, and on forever. And again, one thing to keep in mind here is these series, their signs alternate. So not only is it an infinite series, it's an alternating series. Plus, minus, plus, minus, plus. Again, cosine, plus, minus, so on and so forth, right? Now, why am I showing you this? Because I'm going to make what's called a small angle approximation. Let's not worry about the cosine right now, because what we have here is a sine. I want to try to linearize. So I'm going to assume small angles. We're going to make what's called a small angle approximation. So I'm going to assume theta is small. Small. So if you take something that's small, let's just say, for instance, I don't know, I'll call it 0.1. If I take 0.1, if I take a power of that, I get something even smaller, right? If I take 0.1 squared, that's 0.01. If I take, like in this case, cubed, 0.1 cubed is 0.001. So if I cube 0.1, which is a 10th, I cube it, I get 1,000th, right? And so I get really small, really fast. So if I make a small angle approximation, what this is telling me is that the cube and the 5th power, so on and so forth, are really going to be small. And they're going to be so small that I can actually neglect these higher terms. I can truncate right here. And I can say that all I care about is the first term. So that if I make a small angle approximation, all I can say is that I can say the sine of theta is about equal to theta. So if you put your calculator in radians, and you take the sine of 0.1, you'll get a number pretty close to 0.1. So the sine of theta in this approximation is about equal to theta, and I can throw away all the higher order terms because you have cubes and fifth powers and so forth. Not to mention you're dividing by these bigger and bigger factorials. So for a couple different reasons, these higher order terms can just be neglected. We can just ignore them. We can just say instead of sine of theta, I can replace that with just theta. Of course, theta must be in radians. Makes no sense to put it in degrees. So what does that do to my nonlinear differential equation? I'm going to make the small angle approximation. All right, so let's do that. What does that do for me? Well, that means instead of having a sine of theta, I'm just going to write theta. So I'm going to have that MA tangential is going to be negative mg theta. I'm just going to, instead of writing sine of theta, I'm going to use a small angle approximation to write theta. Now let's remember our arc length formula, right? Because this thing is sweeping out an arc. So S is L theta. Remember, arc length is the radius times the angle subtended. So instead of writing theta, let's do this. Let's write that theta instead. We know that's S over L. So mass times acceleration tangential is negative mg over L multiplied by S. This should look familiar to you. All right. So this is a inertial force. So I can actually write this to help you. Force is negative mg over L times S. Okay, what do I have here? Force is negative constant times displacement. Have I seen that recently? Yes, I have, haven't I? I just got done telling you about a mass in a spring. Mass in a spring that's force is negative kx. That's Hooke's law, right? Let's see here. Force is negative constant times displacement. Force is negative constant times displacement. I have what is called a mathematical isomorphism. I have the exact same math problem. They don't look alike, right? Mass in a spring doesn't exactly look like a pendulum. Mathematically, they are absolutely identical. That means that every single thing that I said about the mass in a spring, every single thing, I get to say the same thing about the pendulum for free. I have what's called a mathematical isomorphism. So the pendulum is mathematically isomorphic to the mass in the spring. The simple pendulum is mathematically isomorphic, is the official term. Means same form. To the mass in a spring. This means that everything that I said about the mass on the spring problem applies to the simple pendulum. So that's very beautiful when you see that in mathematics. These are the exact same problems, right? So what's one thing I can do? Well, remember back in the simple pendulum, I told you what the period was, right? So let me Let me just see that. So again, as I said, the simple pendulum is a mathematical isomorph. It's mathematically, sorry, isomorphic to the mass on a spring. Means that everything I said about the mass on a spring equally applies to the simple pendulum. So, what's an example of that? Well, an example would be I wrote down a bunch of formulas for the simple pendulum. I get those for free for the mass in a spring. So what's an example? Mass in a spring, I told you what the period was. The period, I said it was 2 pi squared m over k. Well, my k for the pendulum, my k in this case is mg over L. That's my k. So let's see here. Period for the pendulum, 2 pi square root m over k. My k is mg over L. Or and interestingly speaking, the m's actually cancel out. So I can actually write down that the period of a pendulum is 2 pi square root of L over G. Period of a pendulum. I get that for free. Okay, so again, this is why I'm being very careful. You want a formula that looks like this. This is the period for a mass on a spring, going back and forth, mass on a spring. This is the formula specifically for a simple pendulum. And what's interesting is that it does not depend on us. It doesn't matter what the mass of the bob is. It doesn't really depend. And again, the idea is small angle approximation. Well, small angle in reality, that means that theta is about less than or equal to about 20 degrees. If that angle is less than or equal to 20 degrees, the small angle approximation applies, and you see simple harmonic motion. You find out that if you try, if we actually did the face-to-face experiments, we would do this pendulum lab, and we'd find out that if we tested for angles larger than 20 degrees, we would find out that we did not follow simple harmonic motion. No, we would violate that approximation, so we would not see that. We would see that we would not actually have that. What other formula might I have? Well, I could say that the frequency, the ordinary frequency for the pendulum, I would divide. F is 1 over t, so I'd say F is 1 over 2 pi square root G over L for the pendulum. Or I can say that omega is just the square root of G over L. Angular frequency. These are all equations that I get for free for the simple pendulum. All right. Just because I have shown it as a mathematical isomorphism. Again, the pendulum at angles where that theta angles is less than or equal to around 20 degrees. That usually is where the small angle approximation will hold. All right, let's work some problems to get ourselves good with the simple pendulum. So let's see. Let's go and test out these new formulas. Simple pendulum. I'm going to look at OpenStack 16.22. That says, what's the length of a pendulum? It has a period of 0.500 seconds. Okay, so what do we know? Well, we know what the period is. We're told that. And we want to find the length of that pendulum. So I go to a formula that we know, we derive for the pendulum. T is 2 pi square root L over G. So what I can do is I'll just kind of flip the equation. So I have 2 pi. Let's just write it over here, I guess. 2 pi square root L over G is T. Again, I've done this before. Again, square root of L over G is T over 2 pi. And continue. Square both sides. I have L over G is T squared over 4 pi squared. Let's multiply both sides by G. I get that L is G T squared over 4 pi squared. And we can plug the numbers in. L, let's see, am I still there? All right. L equals 9.80 meters per second squared times the period 0.500 seconds squared divided by 4 pi squared. I find when I do that calculation that L is 0.0621 meters, or L is 6.21 centimeters. So if I know, again, the only thing that matters for a pendulum is its length. I mean, obviously the planet you're on as well, if you're on Earth, then you get the gravitational acceleration. Okay. Let me do OpenStax 16.25. Okay. How long does it take? A child on a swing to complete one swing if her center of gravity is 4.00 meters below the pivot. So we're going to turn her into a simple pendulum. Again, she's going to be going like she's going to be going like in a translational motion. We're going to assume that all of her mass is going to swing as if all of her mass is located at the center of mass. So here's the pivot. And she is nothing more than a simple pendulum. It's going back and forth. All right. And this is her mass. And we're saying that the length from the pivot to the her center of mass is L, and we're being told that L is 0.400 meters. So we're going to turn her into a simple pendulum. All right. And so how do I do this? I'm going to erase the board here. Okay. Well, we want to find the period. And again, we know L. L is 4.00 meters. So it's a fairly big swing. Okay, T, we can go straight to the equation. T is equal to this, T is 2 pi square root L over G. I mean, it's interesting. All we have to know is the length of this pendulum. That's all we need to know. So 2 pi square root 4.00 meters divided by 9.80 meters per second squared. And we quickly find out that the period of her motion back and forth will be 4.01 seconds. That means she'll go, from far cocked in one direction through straight down all the way to the other direction and then right back up to where she started. All of that takes 4.01 seconds. So again, starting from some point, going through an entire cycle, getting back to the original location, getting back to the original configuration, that's what we call a period. The time for one entire oscillation. All right, let's do another problem. I'm going to do OpenStack 16.29. Okay, this is interesting. You can actually take a pendulum and use it to measure the gravitational acceleration. And again, we use an average. We use an assumed 9.80 meters per second squared for a perfectly spherical Earth, but the Earth is not perfectly spherical. It's called an oblate spheroid. It's fatter in the middle than it is at the poles, and really by about 8 miles. And we understand why this is so, because when the Earth was forming, it was rotating. And so because of centripetal force, it got, there's more centrifugal force, if you will, the inertia pulled more mass out near the equator than at the poles. So it became pear-shaped. So that's before the Earth had cooled, during its original formation. All right, so 16.29, a pendulum with a period, we can be really accurate here, of 2.00000 seconds. I'm sorry, we need to be very precise. In one location, and G at that location, we understand to be 9.80 meters per second squared. Is moved to a new location. Where the period is now 1.99796 seconds. What is the acceleration of gravity at the new location, at this new location? So what is the acceleration due to gravity at its new location? All right, so this is pretty cool in that you can take a pendulum and you can look at the motion of a pendulum and determine the gravitational acceleration of wherever you go. So we know, so I'm going to erase. So again, I'm going to erase this and let's kind of look at the English here of what we know. So we know the pendulum characterized in a place, where we know the acceleration of gravity. So we say, well, at our initial location, we have G0, our home lab, for instance. We know that right there, the acceleration of gravity is 9.80 meters per second squared. And we know that if we test the pendulum right there, it's going to go exactly, we've got it nicely calibrated to go exactly 2.00000 seconds. That's period, right? Now, it's the time it takes a pendulum to be fully to the left, going straight, fully to the right, straight vertical, and right back to the left again. One whole oscillation, back and forth motion will occur in exactly 2.00 seconds. I'm sorry, 2.00000 seconds. Now we're going to move the pendulum someplace else. We don't know what G is at its other location. We do not know. But we do know that if we take this exact same pendulum, that pendulum will read a T1 of 1.99796 seconds at that new location. So we can take the same pendulum, same length and everything, put it in a new location, look at its period, and determine the gravitational acceleration there. It's a pretty cool way of measuring gravity. So how do we do that? Well, we know the period. We know T0 would be 2 pi square root L0 over, or actually L over G, because we're using the exact same pendulum, right? So pendulum has length L, that doesn't change because that's a constant. And we also know the new location, T1, is 2 pi square root L, same pendulum, same length, over G1. Okay, so what's constant here? 2 pi times the square root of L. Well, let's set both equations equal to that and eliminate the constant. So if I take 2 pi times the square root of L, that's equal to what? Square root G0 times T0, or square root, we'll say T1 times the square root of G1. It's also equal to T0 times the square root of G0. All I've done is set both equations equal to 2 pi times the square root of L. And for me to do that, I had to multiply it over by square root of G0 or square root of G1. So I'm eliminating 2 pi square root of times the square root of L, and I'm now left with just this equation. And what do I want to find? I want to find G1. Let's square both sides. So I get G1 T1 squared is G0 T0 squared. And I now just want to solve for G1. So G1 is equal to, I have T0 squared over T1 squared. Yeah, glare there. I'm going to write it up here. So I'm going to erase this stuff. All right, G1, solving this equation. G1 is T0 squared over T1 squared times G0. Plugging in values, I get that G1 is 2.00000 seconds squared divided by 1.99796 seconds squared, and all that's multiplied by 9.80 meters per second squared. When I do all of that, I will find that I will have a G1, gravitational acceleration due to acceleration due to gravity at this new location will be 9.82002, or actually, well, I just need to, I can keep it to just 3 signals. So 9.82 meters per second squared. And there you go. So it turns out that at that location, the acceleration due to gravity is 9.82 meters per second squared. Okay. So in our life, we realize that we really never see simple harmonic motion. That it really ends up dampening out. You know, let's say for instance, you know, you go to your house and near your door, a lot of people have on their wall, they have a little springs that protect against the door slamming into the wall. So you accidentally kick it with your foot, you know, that little spring that's kind of near your floor, it's going, it, you know, it makes a little sound and it quickly dies out, right? And so we know that a spring just dies out eventually. You disturb it or you perturb it, it's eventually going to die out. So we want to actually model that. Now that dying out of the spring is called damping. So damping so damping is the type of friction in a spring. Now again, we're talking about a new type of friction now. The only friction we've been talking about so far is sliding friction. Now we're going to talk about this kind of friction that's inside of a spring. It's called damping. All right, so it turns out that the damping goes as the velocity. So I would say the damping force goes like the velocity. We can oftentimes refer to it as, again, it's going to be a force that's going to oppose the motion. So we would say it'd be like a negative mu times the velocity of the mass, or we could say that the damping force goes like negative mu dx dt. All right, so this is mu is a damping coefficient. All right, and so we say that there's this. I can't derive this. I just know experimentally that this is how this damping force, this frictional force of the spring goes. That's the form of it. It's an empirical relationship. You can set different damping coefficients, but again, there's nothing to derive here. So I want to go back to Newton's second law again. I want to put this contribution in. So if I go back to Newton's second law, knowing this contribution, we return to the differential equation from Newton's second law, and account for damping. What do we get? Well, what is Newton's second law now? You know, what's that differential equation? Well, we saw that we had second derivative of x with respect to time, and we had plus, or well, we had a plus, I would say omega squared, omega not squared, I'll say, x equals 0. Let's actually make this explicitly a function of time. So let me kind of write this a little bit differently. So the second time derivative of x explicitly as a function of time, plus omega squared, I'll say omega naught squared, remember I'm going to call it a natural frequency for something we'll talk about in a moment, times x as a function of time equals 0. That is the superharmonic motion with no energy dissipation. But I got to add a term now to account for damping. So it turns out that if I do that, then I got to add a term in here that will account for damping. So I'll have to add a mu dx dt, and then I'll just have what I had before, omega naught squared x. Again, let's be explicit. X is explicitly a function of time, plus omega naught squared x is a function of time is equal to 0. So what I had before, but now I'm going to account for damping. Okay, so I'm counting for a force that does what? It's a force that depends on the velocity of the mass. It dissipates based upon the velocity. All right, well, what happens now? Well, I have a new differential equation. And every new differential equation, you got to go through the whole process of, is there a solution? And if there is, the existence and uniqueness theorem says that's the only solution. So, you know, you ask the mathematicians, is there a solution to this differential equation? Mathematicians say, yes, there is. It looks like the following. X as a function of time is going to equal an amplitude, constant amplitude, capital X, e to the negative mu over 2 times t times the cosine of omega naught t. Okay, so it looks very much, try to write this a little bit better, looks very much like what I had before, except I had this exponential decay term. Now, this is getting out your exponential function in your calculator now, the e to the x function. All right, so this is cosine of omega naught t. So again, this is basically a dissipative factor, as we call it. So it looks like what I had before, but now I'm multiplying by what's called a decaying exponential. So what does that look like? Well, what it looks like is, well, how do I figure that out in general? So again, so this is what my function, I'll rewrite the function up here. All right, so let's get an idea of what it looks like. Again, this is the function, the equation that I solved. Here's the solution. And I'm not going to prove it. I mean, we're just going to take it as, it'd be more complicated to go and do it, not for this level of class. So again, this is what I'm trying to look at. X is a function of time. Is capital X, constant, e to the negative mu over 2 times t. All that's in the exponential function. Times the cosine of omega naught t. All right, so what does this function look like? Well, oftentimes a good trick to do is say, well, I want to get an idea what this function looks like. So what am I doing? I'm multiplying the exponential function. Decaying exponential looks like what? Well, given time, decaying exponential is going to have some maximum value. No, in this case, it would be e to the 0 is 1, and then it'll just decay towards 0. Never get there, but asymptotically approach it. I'm taking that and I'm multiplying a function looks like this. Yeah, multiplying these two functions together. And this is also time axis. What do I get? Well, I get a picture that looks like the following. So, and I don't forget, I'm multiplying by capital X here. So we'll say positive cap X, negative cap X. I'll start off at positive cap X, but let's kind of get an idea here. I'm basically going to have a cosine bound in an exponentially decaying envelope. And essentially, it's going to just die out. You know, it's kind of like that spring. It's going to die out and eventually get back to the equilibrium position. It's going to die out with an X. So it's going to be basically a cosine function bound within a decaying exponential envelope. That's what I'm going to have. Let me write. So we're going to a little bit of glare here. Some important results. And my answer looks like, and this is exactly what I see experimentally. Yeah, that's what I'm getting. Again, a cosine function bound in a decaying exponential envelope. That is what you see experimentally. You see a function that, you know, it'll essentially mass in a spring. It'll pass the, you know, it'll start off with a full compression. It'll pass the equilibrium, not go quite as far out. Pass equilibrium again, not go quite as far, and eventually it'll just settle. It'll settle on the equilibrium. Start off max compression, pass equilibrium, and it'll just kind of settle eventually at equilibrium, which is exactly what you would notice. Now, this is called, again, damping. Now, sometimes you want damping, sometimes you don't. You know, and so many times in engineering systems, you want to knock out any kind of damping. So, so like in a car suspension. So again, as I was saying, you're going to have extra wiggles, extra oscillations. If a damping coefficient, or if we have a damping coefficient that smoothly returns a perturbed system back to its equilibrium position, or directly back to its equilibrium position, with no extra oscillations, the system is said to be critically damped. Write it down here. And we would say that we would have critical damping, or mu would be mu subcritical. So the mu that corresponds, so again, if we have a damping coefficient that smoothly returns a perturbed system directly back to its equilibrium position with no extra oscillations, the system is said to be critically damped, and mu equals mu sub c. Okay, you want this, let's say, for a car suspension. So what this means is that in general, a damped system is gonna do what? A damped system is gonna give you extra perturbations or extra. So let's say, for instance, you have a car suspension and you hit a bump. And of course, what does the bump do? Well, the bump is like compressing the spring, kind of like what we did earlier. So, you have a damping, and in general, what do we see? Well, in general, we saw, we're going to come back to equilibrium, but we're going to overshoot, and eventually we will settle upon equilibrium. Well, critical damping means you don't overshoot. Critical damping means that if your system is perturbed, you literally just return it straight back to equilibrium as quickly as you can. No extra oscillations. It goes right back to equilibrium. You want this, say for instance, you want this for a car suspension. If your car hits a bump in the road, you don't want to be going, back and, you don't want to kind of feel a little bit of extra oscillations. You want to have that bump in the road, and you want to go right back to your equilibrium position of your car suspension. When your suspension is about to give out, or maybe your car is very old, when you have these little extra bounces. Okay, and that's when you know it's time to get a new suspension. Okay, you don't want that for the passengers and the riders of your car. It's very uncomfortable. So you want to have critical damping. You want to literally have what's called a dash pot in the car. You want to literally design the system so that it dampens out critically, such that it returns the system back to its equilibrium as quickly as possible without extra oscillations. If you get extra oscillations, if for instance, so we talk about mu critical. If we have a damping coefficient, so if the damping coefficient of your system is less than mu critical, it's less than critical damping, we call this system underdamped. So then the system is underdamped. This means that it will not directly return to equilibrium. But will what we call overshoot. And have extra oscillations. Typically, when your suspension is about to give out, your mu is less than mu critical. So you will overshoot. You'll have one or more extra oscillations when you hit a bump in the road. The bump in the road does what? It compresses your spring so that you would go back and forth, right? Well, you want to go not back and forth. You want to go critical damping. That's what you want to do in this case. Okay, that's called underdamped. Let me rewrite that. Underdamped. Okay, critically damped means that the system, mu equals mu critical. If mu of your damping coefficient is less than mu critical, the system is called underdamped. and will overshoot. On the other hand, if mu is greater than mu critical, the system is said to be overdamped. And it may still overshoot. Right? So again, you want to hit that damping just right. If, for instance, you're trying to make something that, like a suspension of your car. All right. And so again, all of that is by adding that extra term in there. Okay, so I want one more topic to talk about. So what I want to do in the most general case is I want to imagine that I may disturb the system at a frequency that's not the natural frequency. All right. And so, for instance, if I do that, I'm going to do what's called a forced oscillation. If I do a forced oscillation, I'm going to take that more, that differential equation I just got to writing out and add a term to it. And so it's going to look like this now. Second derivative of x is a function of time. Okay, plus mu. First derivative of x is a function of time, basically the velocity. This is the second derivative, this is acceleration. Plus omega naught squared x. But now, instead of 0 on the right-hand side, I'm going to have an F1. Some coefficient times cosine of omega t. Okay, so let's remind ourselves, again, omega naught is that natural frequency, square root of k over m. The system can be thought of as a mass on a spring. K is a force constant. Omega, which is generally not equal to omega naught, is what's called the forcing frequency. So I am applying a sinusoidal force. So I have a system that naturally wants to oscillate at omega naught, but I'm going to apply a force that's different than this. I'm going to apply a sinusoidal force that's different than the actual natural frequency. I'm going to basically disturb the system at a frequency that's different than the natural frequency. Okay, so this is called a forcing frequency. Omega is the forcing term. Okay, called a forced oscillation, and it's being done at an omega. I'm being very careful to say that omega naught is the natural frequency. We got in Newton's second law, with the subharmonic motion. Omega is different. They're not equal. Okay. Now, the big question to ask is, well, here I have yet another differential equation. Does it have a solution? And I keep building things up in a more and more complicated way. Well, I asked the mathematicians, and they say yes, it's a solution, but you may not necessarily like it. So again, it's going to look like this. X is a function of time. It's going to equal a capital X times the sine of an omega t plus phi. Phi is a phase factor. So phi is nothing but a phase constant. Don't worry about it. Just tells you where do you start looking at your function, and we can just set it to 0. But let's just not worry about that. But notice that inside of the sine function, first of all, it's a sine function, not a cosine function. Inside of there is omega, not omega naught. This capital X, before, in the previous examples, it was a constant amplitude. It is no longer a constant amplitude. It is now a complicated amplitude that is a function of omega and omega naught. So this amplitude is no longer simple. The amplitude is given by F1 over M, all divided by with the square root of omega naught squared minus omega squared, quantity squared, plus mu squared over omega over M squared times omega squared. All of this is inside of a radical. Okay, that's what I look like now. Let me write this better. Fraction on top, on the bottom, a very important equation. Omega naught squared minus omega squared. Quantity squared plus mu squared over M squared times omega squared. Now, in this function is not only omega naught, but also omega. So we have something more complicated. We have a sinusoidal function that depends on omega, the forcing frequency. However, the amplitude is frequency dependent now. It depends on the natural frequency and the forcing frequency. This F1 is that constant from, the force constant from, or this coefficient. It's a constant coefficient. M is the mass. It's the mass on a spring, and so that's our amplitude now. Depends on omega and omega naught. And in this case, it is a rational function. That means rational meaning fraction. Well, when you have a rational expression, the first thing you have to ask yourself is where can I get in trouble? I.e., where might the function maybe go imaginary, like or where might we have a problem dividing by 0? Well, if we look at this, we have this omega naught minus omega naught squared minus omega squared. So if you think about a special situation that you happen to be forcing the system at its natural frequency, i.e. omega equals omega naught, what happens? Well, the denominator of this amplitude actually gets as small as possible. If you have very little damping, you're talking about a denominator that can get near 0. Dividing by 0 is infinity. You can actually have the system go nuts if you force it near the forcing frequency. Now, again, if I imagine for a moment, let's kind of give an example. Let's just say that I have, let's say my son on a swing. And so he's going on a swing at a natural frequency, his natural frequency. Now let's say I'm being kind of goofy and I'm going to try to push him on that swing at a frequency different than his natural frequency. Well, sometimes I'll get it right and I'll connect with them, and other times I won't. For me, pushing a child on a swing, the best thing I can do would be to push the child at the natural frequency of the child. Every single time the child's back comes, as far back as possible, my hand's there to push. And so my frequency is exactly the same as his frequency. And I have, but doing that is fine for a child on a swing. So when I have a situation where omega naught equals omega, Let me write this over to the right. When I have a situation where omega naught, very special case, omega naught equals omega, that is called resonance. Okay, resonance. Now, resonance is great for a child being pushed on a swing. In general, in engineering purposes, resonance is disastrous. You know, great accidents can happen. You know, basically, you're not gonna get large amplitudes. Your system's gonna break up in a very nasty way if you you know, have your natural frequency in your resonance. So for instance, if I take a look and, you know, just kind of draw some little graphs here. If I look at, you know, what can happen to my frequency, let's draw a little plot of amplitude versus frequency. So I'm gonna draw a little plot here. This is driving frequency or forcing frequency. Driving frequency omega. That's what this axis is. And this is my amplitude. Now it's the nasty amplitude here. So we look and we say, okay, well, we have the situation where we have a special frequency omega naught. Well, if we're looking at small damping, this amplitude gets huge. This is for small damping. Mu being small. You know, if it's 0, I go to infinity. For medium-sized damping, start with that. Medium damping, and it becomes less and less a problem if I have heavy damping. Maybe it's down here. All right, and so, you know, if I have a situation where, for instance, let's say I have an airplane, and, you know, or give me an example. You know, somebody is in the back seat of your car, and they roll the windows down. At least in my car, what ends up happening is I have a very, very unpleasant oscillation sound. It sounds terrible. You know, like my kids will be going at full speed. My kids will roll the window down. I'm like, oh, please close the window, because it says that fluttering sound. It sounds terrible. Well, that's the wind basically vibrating against that little section of the glass. Now you imagine here that you have airplane wings, and let's say the wind will naturally want to vibrate the airplane wing. It's going to vibrate them, right? Just because you have wind going over the wings. What happens if, you know, the wings? You got to allow the airplane wing to vibrate a little bit. What happens though? I mean, I'm just looking at one wing right here, the way what I'm doing my hand. What happens though if I don't design things well, and I find out that air that's going to go over the wing is going to cause it to really flap and then break off? Well, your airplane is carried by its wings. So, for instance, if you design the airplane such that any kind of frequency that might be experienced, let's say by airflow over the airplane, will vibrate the wings near the natural frequency, that's really, really bad. You know, part of, you know, having a PE, as I said earlier, you know, is that you need to analyze this. You need to analyze public safety. You want to make sure that any kind of frequency that your system can possibly experience does not get near the natural frequency of the system. That could be an absolute disaster if that happens. Now, there's a very famous situation in history, and I just kind of want to close my my lecture with this, and that is the famous Tacoma Narrows Bridge. So I'm actually from Tacoma, Washington. And Tacoma, Washington, I kind of oftentimes draw an analogy between Fort Worth and Tacoma. You know, Tacoma is right near Seattle. So I'm going to kind of talk about this for a moment. So Tacoma is near Seattle, and they have kind of a similar relationship. And again, any of my friends listening to my buddies from home, listening to this lecture may not like some of the things I say, but anyway, we live in Dallas, Fort Worth. Let me see how we went through a pin. We live in, Dallas, Fort Worth area, right? And so you look at Dallas, Texas. Dallas is a metropolitan city. It is at the city of any international city, right? So you look at Dallas, Dallas and Fort Worth, they share an airport. No, they share the DFW airport, right in between. Well, we have Seattle and Tacoma over in Washington State. And they share the SeaTac airport. Seattle would be a city that is international, an international major city of the world, like Dallas, like Houston, like Mexico City, Madrid, or Paris, France, Berlin, Germany, so on and so forth. They're major. It's a major city, and then like Fort Worth is more, like I would say, even though it's my home and I love Fort Worth, it's more of a working class town. And same with Tacoma. There's more of the little sister city, if you will, even though they're like twin cities. Well, Tacoma, like Fort Worth has a lot of beautiful things. And Tacoma is all, it's kind of interesting. The northern part of Fort Worth is like your more wealthy part of Fort Worth. Well, the northern part of Tacoma is the more wealthy part of Tacoma. In the North Tacoma area is University of Puget Sound, or Puget Sound. I went to University of Puget Sound. 2 of my 5 degrees are from there. And one of the things you'll notice in Tacoma is a very, very beautiful bridge. And it's called the Tacoma Narrows Bridge. Now, this has an interesting history. And it ties in with what I've been talking about. Tacoma Narrows Bridge has an interesting backstory. So, basically, the Tacoma Narrows Bridge was constructed right around, I think I remember, it was like around beginning of July of 1940. All right, so it opened around, I believe, early July. May have this wrong, of 1940. That is actually correct, 1940. Brand new, and it's an expansion bridge. And it was the 3rd longest in the world at the time. It was second to the Golden Gate and the George Washington. All right. So again, it was an expansion bridge, but one of the things they found out pretty quickly was that it was kind of like going on a Six Flags ride when you went over that bridge. They call it Galloping Gertie. You got a little extra ride as you went across. So again, that's not good. And so people knew that that was going to be a problem, and so they started to study it. And it turns out that the University of Washington, around Seattle area, had a really top-notch civil engineering professor. His name was Frederick Farquharson. Let's see if I got this right. Farquharson. May have his name spelled wrong, but he was actually a civil engineering professor at the University of Washington. And he was looking particularly for failure analysis. And what's interesting about him is, he was originally from Canada. He fought in World War I briefly. Canada would participate in World War I as well. He was captured by the Germans and spent most of World War I as a German POW, and or POW in Germany, a Canadian POW, I guess. So he got out of World War I, went to school, and he went to the University of Washington, and he got his PhD in civil engineering. And he actually was so good that they actually offered him a position at the University of Washington afterwards. So here he is, the prime opportunity to study a bridge that was having problems. And so it's the Coman-Narrows Bridge. And so Coman-Narrows Bridge essentially was, he took his group of graduate students down there, and they studied it. And what they wanted to do is, the Washington State, Public Works, wanted an answer to what did they do about this bridge. So Farquharson had, a couple of different solutions. One of the things he wanted to do is he wanted to drill holes into the bridge to reinforce it. That was potential solution one. The other solution was to create buttresses to help reinforce the bridge. And importantly to the Washington State Public Works is that, and no drilling was necessary. That's what they like. They're like, okay, well, let's fix this bridge, but let's not stick holes in it. All right, and so they came up with this solution. Washington State Public Works says, oh, we like number two. Let's go with number two. But this was this came up right around, I believe it was November the 4th or something like that. And a few days later, a storm hit around Alaska. And there were some high, gale force winds that were visiting Washington State. And what we end up happening here is that we saw the following. So let me share my screen and show you what happened just a few days later. And so let's take a look here. Hang on 1 second. I'm gonna pick one more. I want to pick something here. Try to share my screen again. Yes, I want to share the sound. There you go. Okay, here we go. Sorry about that. Okay, a few days later is the following. All right, so what we just saw there is the complete collapse of the Tacoma Narrows Bridge. And you know, again, there's an interesting backstory with this. I mean, what really happened is that the bridge was not built correctly to encounter any kind of winds that may be experienced, and it just so happens that the gale force winds, basically about 50-mile-an-hour winds, which would be, you know, nothing in Texas, right? But the bridge was not designed right, and those winds happened to have tickled the natural frequency of the bridge, and the bridge went nuts. You know, you see that bridge flapping about like it's a ribbon. That's concrete. That's pavement. That is an incredible amplitude for that to happen. And the bridge was basically ripped apart by nothing else than natural frequency. So you might, you know, you ask yourself, well, what in the world's wrong with these scientists, these engineers, that they would build a bridge like this? Well, the reality is they didn't know how to make a bridge like that yet. Now you're talking about expansion bridge, and you understand it's 1940. 1940. I mean, if you go 20 years earlier, nobody even had a car. You know, you didn't have mass production of cars until right around 1930. So all of this was new. These are growing pains. Because now you have, well, now we got to go across the Puget Sound. We have to make these expansion bridges because now we have cars. You know, it's kind of like cell phones, right? I mean, cell phones. You know, before we had cell phones, you know, not very many people had cell phones. Only your very rich people had cell phones. You had to be really rich to have a cell phone. Then it got to a point where the technology got so that you have teenagers, kids in elementary school that have cell phones now. Now what happens? Well, now instead of just having, let's say, like where I grew up in the Washington State, the entire area code when I grew up was 206. That's it, 206 area code. And now you have 206 is just nothing but Seattle. Now you have 253, which is Tacoma. You have all these different area codes spread up. Why? Because every family now has 3, 4, 5 cell phones. So now everybody needs a whole bunch of new phone numbers. Now you need new area codes. And that's a growing pain. Now you got to put up cell phone towers. And you have all these, various things. Now you have to accommodate this new technology. Well, cars had to be accommodated. Now you have to have highways. Now you have to have bridges. Now you have to have these expansion bridges. You have to try to make a bridge over a long expanse. And how do you do that? Why? I mean, before you didn't need to do that, but now you do, because people want to, live on the islands and come over and work, work in Tacoma and stuff. So you have to accommodate a whole new technology. So this is 1940. And so the interesting backstory is, one of the things I kind of wondered about is, now again, it's an interesting Wikipedia page on this. I would suggest, it'd be kind of cool to read it. But one of the things I always kind of wondered about is, how did they get this good video footage? Today, everybody is like an amateur photographer or videographer, right? Something happens, they get out their cell phones and they start recording, right? Well, again, this is 1940. Nobody had the ability to make a video at that point in time, right? And so I thought that my original thought was that Dr. Farquharson probably contacted the Tacoma News Tribune and got them out there to go and video the situation. It turns out that's not true. Turns out, just by happenstance, that a couple of, just down the road was a guy who owned a video shop, or a camera shop. And so he decided to take one of his cameras, and he happened to be, not only did he sell cameras, he was actually quite good at using cameras. So he went down there, and so here you have a bunch of lucky things happening. You have Dr. Farquharson right there when this is happening. And then you happen to have a guy who owns a camera shop just down the road who's able to film the whole thing for posterity. And so this bridge all fell into the Puget Sound, and there was no replacement bridge for something like 10 years. Because you got to remember, it's 1940. 1940, we're 1 year away from going to war in World War II. So what they actually did is they took all that material from that bridge and they took it to go and help make warships. And so there wasn't really a replacement Tacoma Narrows Bridge like you have today for a good 10 years. So, and the other thing too, to kind of remind yourself here, is that the growing pains happened for a while. So you had in World War II, you had, 5-star General Dwight Eisenhower. Well, he became president in 1952. It wasn't until Dwight Eisenhower's presidency did you even have freeways. We have this nice network of freeways now. Like you go south, you have 10, and what's going through Fort Worth is like 30 all the way up to like 90, right? And then the crossways 5, 15, what goes through here, Fort Worth is a 35 and a 45. Well, these freeways didn't even exist until Dwight Eisenhower. And so all of this, all of this situation with building roads, well, all of this for, to accommodate cars was relatively new. I mean, today we take it for granted. Today, our culture is, you have, a child reaches the age of 15 and a half, and they get a driver's permit and a driver's license. Well, none of that existed back then. Cars were too new. We didn't have it as part of our culture. And so again, the idea is, today, if you saw something like that happen, yeah, what is wrong with the engineers that made that? Because they should know better. Especially if they have a PE and they have a stamp and they have a seal and they put their seal on that, yeah, this is a safe bridge, and then something like this happens. But one of the things you got to check for is resonance. You do not want to have resonance in your system. You need to analyze that system, make sure resonance does not happen. So again, I find this always a very fascinating. I've probably seen this video 100 times. I've seen it once. I mean, I saw it the first time when I was in elementary school. So today's Tacoma Narrows Bridge you see is completely not the original one. The original one fell apart. And so anyway, I just wanted to point that out. This is an example of resonance. This is an example in that differential equation where you have that amplitude where omega got very close to omega naught. The driving frequency from the wind got very close to the natural frequency at which the bridge would like to oscillate. When that happens, that's bad. It means that denominator becomes very small, which means the amplitude becomes very large. And it literally will break itself apart, which is exactly what you saw there. All right, with that is all I have to say about chapter 10 and oscillations.